All right, welcome to our first lecture in COP 2803 Client Side JavaScript. I am Professor Tillman and I will be your guide. All right, so this lecture we're going to spend a moment and talk a little bit about application architectures. All right, so your first question is going to be, well, what is a software architecture? Well, in essence, whenever we create an application, we have a blueprint, and that blueprint is the architecture. So think about a house. When we build a house in a subdivision like mine, you'll have 20 houses that look the same and 20 houses that look like another house. All right, well, what happens is uh, an architect designs the structure of the house. They design where the door should be, they design where the windows should be, how many rooms it should have, and they build it or they design it based on certain constraints that they may have. For instance, the company may say that we want this house to come in at this price point, and we want it to be able to survive a flood or a hurricane if it occurs. So, given these constraints, the architect will design the architecture that then becomes the blueprint to build houses that, as we say, implement that blueprint. All right. So, the software architecture is pretty much the same thing. A software architect will take in a series of constraints. We need it to run this fast. We need it to run on Unix. We need it to be accessible via the web. And we will take those constraints and we'll also take the requirements for the application. The requirements are essentially what the user wants the application to do. And we'll come up with our blueprint for the architecture for the application. And using that architecture, developers will write the code that is constrained by the architecture or works within the architecture to solve the business problem. Okay? So that's essentially what a software architecture is. So let's get into some of the principles of an architecture. Before we do that, let's take a look at a common application architecture. One of the most common application architectures that you'll run into is what we call a layered application. And essentially, it's taking the functionality of the application and grouping it into layers in such a way that the layers are clearly separated and all the dependencies between the layers go in a downward direction. All right. The reason they go in a downward direction is because we want to build our application in a way that changes in one part of the application minimizes changes in the other part of the application. All right. And because this is not a class on architecture, we're not going to go too far or too in depth into that. Just be aware of that concept of loose coupling. All right. But what we see here is a common architecture where we see that we have the application separated into a presentation layer, a services layer, a business layer, and a data layer. All right. And you may also have cross-cutting concerns such as security, operational management, communication, networking, etc. All right, so anything that's related to the user interface, i.e. the HTML web pages or whatever, we will put in this presentation layer. All right, services are things that give you access into the application. So we may use something like WCF, REST services, or web services to open up our application to outside resources. And those would live in the services layer. All right, business layer, that's the bulk of the application. Those are the entities that we create to do the actual work. All right, so for instance, if we're creating a learning management system for online learning, we may have entities such as student, quiz, lecture, grade. All right, all those things will go inside of the business layer. And the data layer consists of classes that actually shield us from the actual data source that we're using. So for instance, we may want our application to use either a database or a web service or a flat file. If we hard code our code directly to those dependencies, then we're going to have trouble changing it later. Remember that concept that I talked about, loose coupling. All right, so this is where that definitely applies. Right, so what we want to do is put in classes in here that the layers above it depend on. And these classes will shield us from the data source that we're actually using. So it doesn't matter whether we're using a web service or a flat file or a database. The code outside of our data layer has no idea what we're using. They just know about the classes that are in the data layer. All right. Now the cross-cutting concern thing deals with um, things that are outside the core functionality of our system but need to be applied at all the layers. For instance, security, right? We need security at all the layers. Some of the layers may need to have network communication with each other. So we'll extract these components and make them cross-cutting, meaning that they can spread across all the layers. All right, so our key principles, you heard me mention it before, separation of concerns. That's what I referred to as loose coupling, right? We want to separate our concerns. We don't want it all in one big jumble where the presentation layer is also worried, concerned about how to access the database and is also concerned about how to construct a business entity, right? When you lump all that together, then it becomes what we call a big ball of mud or spaghetti code, and it's hard to maintain that. The biggest cost of software development is in maintenance. All right, single responsibility principle. You hear me talk about this a lot in my classes. A function should have a single responsibility. A class should have a single responsibility. A layer should have a single responsibility. That means that that particular piece of code is only responsible for one thing. If I have a method or a function that is responsible for writing a file, that should not also write the file, update the student records, and then also calculate their grades. It has too many responsibilities. It should be responsible for one thing. All right. Principle of least knowledge. All right, that means that component should not know a lot about other components that it uses. It needs the least knowledge that is necessary for it to do its job. And you'll see this come into play when young developers create classes. They have the tendency to put a lot of getters on their classes, right? A class's data should be encapsulated. It should be its own data, right? So if we create private instance variables, what's the goal of creating private instance variables if we're going to always expose it via a getter, right? Then it's still tightly coupled to it, right? So classes in essence should do things, right? So you ask it to do something, you don't ask it for something, right? So that's the principle of least knowledge. All right, dry principle, don't repeat yourself. We want our code to not be repeated in multiple places throughout the system. So if we have an if statement that checks to see if we should calculate the bonus for an employee, we don't want that that same if statement several places in the code, because if it changes, it needs to be changed in all those places. So we have mechanisms that allow us to minimize that repetition, such as replacing that if statement with polymorphism, moving it to one class, okay? Minimize upfront design. This has to do with agile approaches, right? So previously, when I first started development, um, we would gather all the requirements. Then the architect would go through all the requirements and try and design the entire system. And then we start code. And then we realized nothing was right and we have to go back through that process again. So that was big upfront design where we're doing all this thing up front. Well, what we learned was that, wow, by the time we get to the point where we're writing code, the whole problem that we were trying to solve has changed anyway. So now what we do is we try to minimize upfront design. We only want to design the parts of the system that we're immediately concerned with, right? But the only way to do that is if we make sure that we separate our concerns and they're only responsible for one thing, and that they have the least knowledge of other components, and that we don't repeat ourselves. All right. I just talked about some of the design practices that we might use, such as replacing polymorphism with replacing conditionals with polymorphism. But you want to keep design patterns consistent within each layer. You don't want to over in one place be using a design pattern such as a singleton all through the code, but then you solve the same problem in another part of the code using flyweight patterns. All right, and you probably don't know what a lot of the design patterns are yet, but just be aware that there are design patterns that are written and uh, uh, discussed online a lot and in books that solve problems that are common amongst all software. All right, great book. It's called The Gang of Four Design Patterns book. If you ever get a chance to pick up a copy of it, I suggest it. All right, do not duplicate functionality within an application. So an architect is gonna really pay attention to where they assign that functionality at, right? So if I got a piece of the system that deals with the databases, I want to make sure that I put all that functionality in the data layer and not have it in the presentation layer as well. All right. Here's another thing: prefer composition to inheritance. In school, we learn about a lot about inheritance. Inheritance is a very powerful feature. In truth, in the field, we very rarely use inheritance. We prefer composition to inheritance. That means we want to compose classes of other classes instead of inheriting from classes. All right. Always strive to establish a coding style and naming conventions. I make sure that all the developers on my team adhere to the same convention, such as using capitalization for constants, using camel casing for variables with an underscore in front of it. This means that any other developer picking up that code understands, what the other's developer, intent was. So it kind of cuts down on the maintenance burden as we're trying to maintain that code. All right, we want to maintain system quality through automated tools. So what we'll do is use a process called continuous integration. So that means that whenever a developer writes code, we have a set of unit tests that test the code that automatically runs when they check in the code. So as soon as they run that code, I know immediately whether something's broken and whether they need to fix it. So we don't want bugs to propagate and find their way to the deployment and be shipped if we can catch those problems up front. So we attempt to maintain system quality by using automated, test tools that we'll actually talk about in this class a little bit later on. All right, and consider the operation of your application. You want to think about the environment that your application is going to be running in. Is it web-based, server-based, mobile, etc.? All right. Don't rely on internal. Sorry. Separate the areas of concerns. All right. So we want to make sure that, again, responsibilities are separate. So that's why you saw in this earlier slide, you saw the concerns being separated into separate layers. All right. Be explicit about how layers communicate with each other. Generally, we'll define interfaces that allow the different layers to communicate with each other, and not depend on an app, on a concrete implementation of a class. That's another concept, dependency injection. We really won't get into that concept in this course, but be aware that dependency injection is a very important topic. All right, use abstraction to implement loose coupling between layers. So that's what I was just talking about. Whenever a layer wants to communicate with another layer, it should talk to an interface versus a concrete class. That means that we can vary or change the implementation easily if we so choose to. So imagine a system that needs to send a notification. Well, if I create a concrete class, email notifier, and my code talks directly to that email class, what happens when I want to send out some use Amazon's notifier service, right? I can't use both, right? So what I do is make my code talk to an interface such as iNotifier, so that way I can replace it with an email notifier, an Amazon notifier, or whatever I choose to. All right. Do not mix different types of components in the same logical layer. That essentially means don't put presentation layer components and database components in the same presentation layer or vice versa in the same data layer. All right. Keep the data format consistent within a layer or component. Uh, don't represent money as a double in one place and change it later on to be a float in another. All right. Be consistent with those data formats. All right, don't rely on internal details of other components. That just means that a class should not know about the internals of another class, just like one subsystem, right, should not know about the internals of the other subsystem. And how do we facilitate that? We talk via interfaces, all right? And that's what the next bullet point also deals with. Keep cross-cutting concerns abstracted from the business logic. Again, use interfaces for security, use interfaces for logging and notification. Don't use concrete implementations. All right. All right. So, what are the major decisions that we have to think about when we design an architecture? Well, this is the key part that determines whether we're going to use HTML, web pages, or whether we're going to use web services, or we're going to use Android. All right. First thing we need to know is what type of application we're building, and that's really going to be determined by the stakeholders, right? So, if they say, well, uh, most of our users are using mobile devices and want to interact with us via their mobile device. Well, why would I create a desktop application if I know that the primary use case is via a mobile application? So I need to take that into consideration when I'm designing an architecture and determining what tools we need to use. All right, determining deployment strategy. How are we going to get it to the customer? Um, for instance, I developed an application one time and we used Microsoft's one-click tool, which means that anytime we create an update, users could easily go to a particular link and download the latest version of the application. All right, determine the appropriate technologies. Are we going to use Java? Are we going to use C Sharp? If we know that the customer has Unix servers, well, then we can't write the application in C Sharp and expect that they're going to be able to run it on their servers. All right, so we have to keep those type things in mind. We have to determine what the quality attributes are. Our quality attributes are things like how scalable does it need to be? Does it need to run on one server? Does it need to run on 3 servers? Do we need to be able to scale up to 20 servers and run? How fast does it need to run? If I'm working on a garage door opener and somebody goes under the garage, how fast should it stop from closing? Okay, and then also determine what the cross-cutting concerns are that we need for the application. All right, so that is it for our brief introduction to the key principles of software architecture, and I look forward to seeing you again. Take care.